Hello everyone, welcome to Anubhav in Tech. Today we'll be discussing a very beginner-friendly system design problem called URL Shortener. It's a very well-known and established design problem, especially asked to tenured SD1 and early SD2s with less than 3 years of experience. And this problem might be a very first system design problem for many. And if you're liking my content on system design and want to motivate me to make more such beginner-friendly and advanced concept on it, do like and subscribe my channel. That's really motivating and help me push further. Also, if you are someone who likes reading rather than watching videos, we have a website for you called Interview Club, where we are posting really great content on system design. And this is the problem which we have already posted. And if you like reading rather than watching, you can check out this website and we'll be doing the exact system design problem which is mentioned here. Okay, let's come back. So the problem is you will be given a long URL and the system is expected to return a shortened URL. And when someone visits that shortened URL, the shortened URL redirects you to the original URL. Pretty straightforward, right? So if you don't know and are very new to this concept, let's quickly check out this website called Short URL. So I have given the long URL, it has given me the shortened URL. If I copy this URL, try to visit, it will redirect to me the original URL. Straight, clear. So this is the point when the actual system design interview starts. You are given a problem and rest is all to you to figure out. So any system design interview, we always start with asking clarifying questions, collecting the requirement, which is functional and non-functional requirements. So we'll start with functional requirements. So the very first functional requirement is a user submits long URL and gets back a shortened URL, basically the short one. User submits long URL, gets back shortened URL. Pretty straightforward. And the second functional requirement is, you can pause the video and make a guess if you're new. That is redirection. Visiting short URL redirects you to long URL. Correct? And then you can ask your interviewer, do we need the client, the customer, to set custom alias? When I say custom alias, it means, are we allowing the customer to choose what the shortened code he or she can pick? So in a way, instead of this random generated code shortened URL, this domain will be same, but the shortened code, can he choose? Can he pick something like Diwali sale? Is it allowed or not? So you can confirm, but in this system design, we'll keep it optional. Optional custom alias support and auto generated codes by default. Perfect. And then also a very obvious question that comes into any one of our mind is, what should be the expiry of this shortened code or shortened URL? Do we need to support, like, it shouldn't be deleting forever? It lives forever, or we need to set an expiry? So for this system design video, we'll keep it optional. So we'll say optional, the user can set optional expiry per URL. Each URL it create, it can select when the shortened URL should expire, maybe an year after, or after 6 days, or after 2 years, 5 years, 10 years. But by default, it should be never expiring. Never expire. Perfect. These are some of the functional requirements which are pretty straightforward. And again, you can discuss some of the functionalities which are out of scope. And I would request you to come up with some of the out of scope functional requirement and mention those in comments. Now the time is to discuss non-functional requirement. Take a pause of video and think of what are the non-functional requirement for this kind of system. So the very first non-functional requirement is uniqueness. Uniqueness, two different long URL should never get the same shortened code. That is like the core non-functional requirement. So two long URL should never get same short URL or code. And this is pretty straightforward, right? Which is like one-to-one mapping. Every shortened code exactly has one long URL. But here's a catch. One long URL can have multiple short URLs. So it is like one-to-many is possible for long URLs. You can constantly create but the system should be able to handle this, and it's a very good non-functional requirement that you can discuss with your interviewer. Do we support creating multiple alias, or basically multiple shortened URL for a long URL? Is it allowed or not? And our system will say yes, it is allowed, and we'll discuss it later if time permits. Okay. And the next non-functional requirement, which is very important, is like redirect latency of short URL should be less than, say, 200 milliseconds. Why? We want to make it instant. It should be like real time. And then we want our system to be highly available. Now your interviewer can poke you and ask why. Why did you choose, and why did you even say high availability? Because if you don't talk about consistency here and directly flex saying high availability, eventual consistency, low latency kind of thing, you might get honey trapped. So always put the rationale behind it. We'll discuss the answer of why high availability and not strong consistency, because we have CAP theorem, right? I mean, our system should be partition tolerant. If you haven't seen my CAP theorem and Packel theorem videos, which is very, very important for while designing a system design interview question, do check it out. Perfect. So our system should be highly available. When I say highly available, a broken shortened URL breaks the link ever. I mean, whosoever has that URL, it will break. It will work for none. So we want our system should be highly available so that it always serves the traffic. So let's say 4 P's availability. And then the scale. I mean, this is a very important non-functional requirement which should come up very initially while doing requirement gathering. What is the scale that we are working for? I mean, at what scale this product will be shipped? How many users will be using it? How many active user, daily active user, monthly active user, and what will be the total amount of shortened URL that we'll be doing in a, let's say, 10-year of span. So we'll talk about scale. For this problem, to keep it within the SD2 and tenured SD1 boundary, we'll say the scale is 1 billion URLs, 1 billion URLs in total for maybe, let's say, lifespan of this product, or let's say for 10 years, safely for 10 years. So the system will be shorting 1 billion URLs in 10 years, right? And also we can safely say that our product, our system, will have roughly around 100 million monthly active users, which is MAU. Monthly active users, right? And also, and it is pretty evident, and this should come up during the requirement gathering, and your interview will likely tell you that the system is read heavy. You can expect 1,000 reads for one write. So it means we'll be seeing 1,000 to 1 ratio of read writes. So for every one write, there can be 1,000 reads. So this clearly sets the picture that our system is read heavy, and we have to design in such a way the system is scalable enough for even 10,000 write for a single write. And it is also clear because user will be creating less URL and visiting more, which is pretty obvious for this kind of systems, right? And then we can point out some out of scope requirements like click analytics. You can discuss with an interviewer, do we need click analytics for this? I mean, it could be optional, but good to discuss. Optional, but like, do we need to support click analytics? Do we need to talk about user accounts, auth, spam detection, multiple such things? We'll keep it out of scope. But I would like to come back on click analytics. I'll talk a little bit about it, how the system can be scalable to support click analytics as well. But we'll keep it optional. Perfect. Now it's the time for capacity estimation, which is popularly known as back of the envelope maths. Okay. This is very important discussion in any system design interview. Why? Because this sets the bar high. This will, if you are not discussing or skipping capacity estimates, basically how much storage we will need, how many, based on the numbers that we discussed in non-functional requirement, which is like for writes, we have 1 billion URLs for, let's say, over a span of 10 years, then how much storage we'll need to store these what will be the data model, right? And for reads, how many, I mean, you need to discuss some maths and come up with how much capacity will be needed for the system. I mean, for this problem, it's pretty straightforward, but it can go complex with increasing difficulty, or maybe when you're asked to design crazy problems like newsfeed, Ticketmaster. In such cases, capacity estimate will be complex, or even while designing Dropbox, S3. Cool. So do this math out loud. I mean, speak out loud while doing this maths. Don't murmur, and be very clear while explaining this in the interview. It takes just 2 minutes, but it is very important to do capacity estimate. So in such case, we'll talk about writes. So writes, so as mentioned, our system has to support 1 billion URLs to be created over 10 years of span. So which is like 1 billion URLs over 10 years of span, which is like 1 billion has 9 zeros. We need to divide this. Basically, I am calculating how much QPS we might be receiving for writes. Based on the QPS of writes and reads, we'll see how much storage we need, and we build this eventually. I want to take it slow so that everyone understands. So 1 billion URLs over 10 years, which is like 1 billion divided by, to get QPS, which is like queries per second or transaction per second, how many writes we'll be seeing per second, we'll divide it by 10, which is like year, and then multiply it by 365, multiply it by with number of seconds in a day is 86,400. Yep. And you'll get roughly around, this maths will lead to you 3 QPS, which is like, you might see, that's an average number, you might see 3 long URLs getting shortened every second, which is like 3 new URLs every second. We'll say QPS. And similarly, as discussed, reads will be what? 1,000 times. I mean, we just discussed, right? We'll see the ratio of reads to write is 1,000. So we can say 3K QPS for reads. Estimate. Okay, now pause on this number first. 3 writes per second, about 3 QPS, which is essentially very less, right? I mean, the write path is not at all challenging. The read path is where the actual traffic you're seeing, which is like 3,000 reads per second, which is huge, right? So how much storage we need for this? Let's do a quick number. Let's say we have 1 billion rows. We want our database. Let's say we choose, let's say DynamoDB, Postgres, Cassandra. Any database will work here, because the structure that we want to store is pretty straightforward. I mean, any database will do the job, right? Any database will do the job. Even if you start a single instance of Postgres on even on your laptop, on your local host machine, even that can serve this much traffic. So 1 billion rows. Let's say each row each row is a mapping of long URL to the shortened URL, right? So let's say each row takes around 500 bytes. Each row takes around 500 bytes per row, which could be, let's say we are storing the long URL plus the short code plus the timestamp, basically when it was created. So this will roughly come around 500 GB. Very less. I mean, not at all problematic. I mean, 500 GB will fit comfortably in a single Postgres or in a single MySQL instance. No sharding, no exotic database, and saying this out loud in an interview for this problem is a green flag. I mean, juniors, especially the SD ones, might overcomplicate it by saying we need sharding for 500 GBs, we might need to do clustering, distributed databases. No, not at all required. That's overkill. And then the another important discussion here is, we saw, right, basically here, this is a shortened code, right? And the length here is 5. We need to decide how long must the short code be so that it fits our 1 billion number of shortened URLs, right? So how long should be the code, shortened code? This is a very important point to discuss. For this use case, we'll use base 62, which is like, why base 62? 62 is the number of character possibility that we can put in a single digit. I mean, in a single, basically the probability. So we'll use 0 to 9, 0 to 9, A to Z and capital A to capital Z. If you sum it total, 26 plus 26 plus 10, it comes 62. So base 62 URLs will use these safe characters. I mean, whenever, and if let's say if we choose the length of 5, let's say if we choose 5 character length, what is the number of possibilities, how many codes we can generate with it? Which is very simple, 62 to the power 5. And if we do the maths, it will come around 900 million, somewhere around 900 million, which is not enough. I mean, this is the amount of possible base 62 URLs that you can generate from it. We are not using any special characters. The idea behind using base 62 is that the URL works very differently, right? Even if I start using special character, anything other than these safe characters, this question mark, this hash plays a different role in a URL, right? I mean, it's pretty straightforward. So we'll skip those. So base 62 is pretty obvious and pretty intuitive. This might question come into some head, so I just wanted to clarify. So this is not enough because we want 1 billion URLs to be generated over 10 years of period. So we'll say 6 characters. If you do maths with 6 characters, this will come around 56 billion, which gives enough headroom to us to even grow further. We asked for 1 billion, but with just using 6 long character of base 62, we can have up to 56 billion unique URLs. Perfect. So 6 characters enough. And if the interviewer bumps you that the scale to 100 billion URLs, I mean, say, no, not 1 billion, 100 billion. We want to scale to 100 billion. You can safely say 7 character would be enough because 62 to the power 7 is somewhere around 3 trillion. Some maths, just one more character. So the two takeaway from this is, one, the system is read heavy, and the second, basically take away from the capacity estimate. And the second takeaway is like 6 character of base 62 will comfortably fit our use case of 1 billion short URLs. Perfect. Let's move to the high level design. Okay. So we'll start with the designing the architecture of this problem. And we'll start it very simple. We'll start with one server and one database. And we always start with designing with single host machine and maybe with single server. And then we'll talk about how and when do we need to scale these. And this architecture will be easily able to handle, let's say, 10, 100 or even 1,000 users. And you can discuss with your interviewer. So the architecture is very simple. You have your client, the user who's trying to shorten the long URL, and then you have your server which does route the request to your, let's say, PostgreDB, and you create a new row in that table. Basically, this server has few jobs. One is first to get the shortened code, right? Short URL, basically to convert the long URL to a short code and then return back. Create an entry in your database, basically mapping out long URL to shortened URL and get back the short code. Perfect. Sounds straightforward, right? And we'll discuss on how the server generates the short code. It's a great question. We'll solve in a moment. But this is how the architecture will look like. I mean, in this PostgreDB, you will store something like short code and long URL, maybe timestamp. That's it. Enough. Yes, and then we'll return the shortcode, which could be, let's say, sho.rt, it's my favorite, / let's say anything, 22. We decided one. Any short URL. Perfect. Right? This is what the users get back in return, and this is what we saw. We gave a long URL and we got a shortened code. Perfect. Now your interviewer will start poking you and asking, how do we generate the shortcodes? I mean, that never repeats. I mean, we need to guarantee one of the non-function requirement, right? That every long URL has a unique shortened code. Imagine where 2 long URL gets a same shortened URL, shortened code. This is essentially collision, which we don't want it to have. That essentially breaks our system. So that's the core part, and your interviewer might be interested in knowing how we generate the shortcodes, and then which redirect do we return the HTTP? Is it 301 or 302? And then also he might be interested after this, he might be interested in knowing it, how do we keep the redirect at 3000 QPS fast? Because in this case, what we're doing, whenever a new request comes, the server will check in our database for a shortened code, get the long URL, and then return back. This is how the read path will work. Client request, the server looks up for the shortcode in the database. If it found the mapping, it will return back with an HTTP redirect to the original URL. otherwise not found, which is 404. Now we'll dive deep on how do we generate the shortcode. The very simple solution could be getting prefix or suffix of long URL. This solution is very naive and must be avoided discussing during interview because it fails immediately. And I want you to comment down in the chat and let me know why it fails. And I don't even want to explain it because it's pretty straightforward. And if you say this, you should have an immediate solution after this. The second good solution is, which is very again intuitive and that might come in someone's head, hey, hash the long URL. If you know how hash maps work internally, you know the same concept can be implemented here, which is hash the long URL. Okay, this is a great point. Instead of doing prefix or suffix, choosing a prefix of, let's say, we decided that we want six character long shortcode. We committed upon that, right? So prefix of length 6 or suffix of length 6, that won't work. Instead, one can run the long URL, URL through a hash function. A hash function like SHA256 or MD5. Perfect. So I'll give you a live example of SHA256 generator. So let's say if this is a website which helps you generate SHA256 code. So let's say if I enter the long URL, hit generate, you will see a 256 SHA256 hex generated, right? And you can read about it. What does it mean? Here, essentially, what we can do, take the first 6 prefix, or instead you can use an MD5 generator as well. Now, you might say, oh, that's good, because this helps me generate unique SHA256 hash. It always gives me a unique hash and it's deterministic. Does my job, but there's a problem. And again, I want you to comment down and let me know why this is a problem, and it's a major concern. I may throw up a hint for this. Too long URL, because here we are only taking the first 6 characters of the hash that we have got. Too long URLs might still end up having the first 6 same, and you can do a debate on this, and there's a maths that supports the fact about it, that why there will be collision very sooner than you even think. Just to throw up, you might start seeing collisions after 2 lakh, let's say 2 lakhs of long URL conversion. Which is bad. And I know we can do some work around here. You can say, Anubhav, I know we can lead to collisions here. This is I know this can be exploited. So we can add some salt to it and again generate and again do a lookup in our database, which is here. Basically, we'll try to generate a new hash code which is not available in our database, which is new. So we'll again add some salt, again hash it, and we'll repeat it until we get a unique one. And then there's a trade-off. This will take good compute, right? And then you might say, for fast reads, you can introduce Bloom filter so that we can efficiently check without querying our database every time we try to generate a new hash by adding the sort. I know this can be complicated, but give it a moment and you will get it. Okay. Some of you might have already a solution, and I know, which is using a counter with base 62. We initially talked about base 62, right? Let me quickly open a base 62. Okay. Why base 62? I mean, because we want to avoid using special characters and we just want to use digits, alphanumerics, right? So basically just counting with 62 symbols instead of just 10, which is digits. And the same way the hexadecimal counts, right? Which is bit 16. We have more space here, more probability. So any number we can map to a base 62 encoder, right? We can encode anything to a base 62. So let's try it out and see. So let's say we have a counter which increases every time there is a new request for new long to short URL mapping, right? So let's say the very first request hits and the counter is 1. You do the encoding, you get the value n. Your counter increases 2. Now the next request came to create another long to short URL mapping. You'll again do the encoding, you'll get O. Similarly, let's say you have now done 1000, this is the 1000th request of creating new mapping of long to short URL. You'll see another unique encoded result. So this can even scale to any number within 1 billion, right? Every time we'll get a unique response. And this perfectly fits our use case, right? So think it of something like a token counter at SBI Bank. Every customer gets the next token number and no two customer can ever hold the same token, right? Which is what we wanted here. Every long URL is mapped to a unique short URL, right? And no two short URLs are mapped to a single long URL. That's the whole trick. Every number is unique, so every code is unique because the counter is increasing. And the counter can go up to 1 billion and it can even scale further, no problem. So collisions are impossible by design. And the right path is like single insert, right? No check and retry ever the problem that we might face in doing the hashing. And this is a perfect solution. But this design had a problem, right? And this can be fixed easily. The problem is if the server goes down, our counter is lost. And this can happen, right? Because server can go at any moment of time due to maybe high number of requests, network failure, task restart, out of memory issues, anything, or even due to DDoS attack. So if we lose the counter number, that was the what was the last number of unique URLs that has been created so far, it's like miserable. It's a miserable day. And to solve this possibly, we'll decouple the counter logic from the main server, because at any moment of time we might need to scale our server, basically add more number of instances. The Postgres database single instance would still suffice, but maybe the server we might need to scale up because it does some task which is creating the code, doing lookups in table, multiple things, and it can also serve the authentication flow, maybe server protection, throttling, rate limiting, whatnot. So we might need to scale up our servers, right, at any moment of time. So we definitely need to decouple the counter logic from our server. Basically, where do we keep this shortcode? So the answer is to put into a Redis. If you don't know Redis, a very simple explanation is Redis is an in-memory cache, single-threaded. Yes. And in our case, all these servers can have their independent Redis, and we can also talk about how we can, let's say, in any request comes, each server might have its own shard of, or basically not shard, basically logical or let's say virtual partition of number of unique URLs. Let's say server 1 might handle something from 1 to 500 million, and then 500 million to 1 billion number of unique URLs can be served by the another server. And we can do some logical partitioning over here, but that's fine. So Redis will store our counter in Redis. And every time a new request comes, we can use the increment operation in Redis. Since it is single threaded, it gives you consistency out of box. So even if 1000 requests arrives at once, each will get a different number, because we are increasing the counter every time, and it guarantees you. But now we have only 3 QPS. I mean, for this discussion, we discussed that 3 QPS is what we'll receive for writes, and then Redis won't even sneeze for this kind of QPS, right? It's pretty small. Perfect. So now if you want to see how the user flow will look like, this is how something it will be. Client gives you a post request with a long URL. It hits your server, and then you will talk to your Redis, which stores the counter, the global counter. Let's say the counter returns you this value, which is like 10 lakh, a million. And then you insert into Postgres. I mean, the base 62 thing will be calculated in an app server. It returns you this value. You calculate the base 64, which is 4C92. You insert the ID code URL in your Postgres. You return back the shortcode. That's it, simple. So now let's discuss another very important part of this system design is HTTP redirect. Which HTTP redirect to use? And yes, there are 2 types of redirect that HTTP provides, which is 301 and 302. Both tells a different story to your browser. When you return a 301, you're telling your browser that this long URL has moved completely to a new URL, which is a shortened URL, right? So basically, this mapping will never change. Remember it. This is what you're telling to your browser, and browser then caches it in your local browser. Then the another type of redirect is 302, which says temporarily move, right? It doesn't tell the browser to cache it. Let's see the trade-off. Which one to choose basically? 301 is permanent, 302 is temporary. 302 tells your browser that remember this mapping. 302 tells no, don't remember. It's a temporary move. As soon as the first click happens, the next clicks will never hit a server because browsers knows the mapping it has in the cache. It will never reach a server. It will skip your server entirely. But in 302, everything will happen through your server. I mean, every time your request will hit your server, and then you do make a decision and then return back the long URL redirect. Then, can you expire or update the link later? No, because the browser has a copy of it and you have lost all the control. It can only happen when you ask your client or the user to clear his cache, which is a tedious thing to do. But with the 302, yes, we can do. And we can add expiry, we can do analytics, which is like number of clicks per shortened URL, a lot of things. And this is a game changer thing for us. And also load on server. 301 definitely lower load because every new long to short URL mapping will hit only once. Later, everything will be served by a browser cache. But for 302, it's high. But we know the write requests are fine, and we'll see how we can scale for 3000 read request as well. So in this situation, comment down what would you choose. Okay, so my decision is to choose 302. Fine. Our requirements, one of the requirements which is optional, was to have an optional expiry. Remember? Have an optional expiry. Yes, this one. So once a browser cache, let's say 301 redirect, that link is forever with your device, no matter whatever your database says. But with 302, you are in control. You can do changes to it because every request happens through your server. You can fix a wrong destination. You can add or remove the expiry. You can do n number of things. But the trade-off is with an extra load on your server, which comes with a price. And in the next deep dive, let's make the load cheap because with the 302, we'll definitely see higher load on servers. And also it helps you enable click analytics, which is again very important concept and a very important requirement that might come up soon. Okay, now let's do the third dive deep, which is again very important. And we just discussed that we want our system should be able to handle the load because we just choose 302 redirects instead of 301 because that gives better control to each request that we are serving rather than giving all control to the browser. So at 3000 QPS, 3000 write QPS of redirects, and yes, we discussed it here, right? 3000 QPS of reads that we might be seeing and 3 QPS of writes. The read path is where all the problem is happening, right? So one solution that might come up straightforward from ahead is, hey man, we are storing, essentially we are doing lookup from the database and we have this schema of short code long URL mapping. Why don't we create a index? Why don't we index our short code column? And the answer is yes. Without an index, data would do an entire scan, right? Entire scan of database of 1 billion rows. Basically, essentially asking which row has this code by scanning all the rows until it essentially matches. So here, rather than that, what we'll do, we'll index, and indexing, I think I don't need to introduce this, what indexing is in a database. If you don't know, check it out. Watch some video or maybe Google it. Once you index, and out of the box, we know that this you will put that unique constraint on the short code. Internally, Postgres uses a B tree and it will save massive amount of time and the lookup will be really fast with just introducing one column. I mean, by introducing or adding index to your short code column, right? Now you might say, Anubhav, that's enough, right? This one fix, or you say this one optimization alone will help us meet our latency requirement, which is like, let's say 200 millisecond or 100 millisecond. Easy peasy for Postgres or any database in real. That the database choice, I mean, yes, you might ask, Anubhav, we have been using Postgres. We didn't discuss about why Postgres, but in reality, any database will do this job, right? It's pretty straightforward. Nothing complex, no wasted transaction, nothing. So do we even need to go further? Do we even need to talk about further optimization? Yes, there can be a slight optimization in the read paths. Imagine some short URLs sees more traffic, basically some hot short URLs. basically some hot links during Diwali sale, or let's say any product comes up and the short URL is viral. Link for those traffic will be much higher than the normal ones. Basically, it will create a skew in the reads. To overcome this, we can have again Redis. Why? And it is pretty straightforward. It's a cache. You will store all those hot links in your cache, have an eviction policy. All those hot links will never touch your database, rather will have Redis sit in our read path, right? And serve the request back. Yes. So now let's see how the user flow, basically request flow, might look like with the final architecture that we have right now. We'll also discuss with the eviction policy how much TTL we might need to have, what kind of safety we want to put. But for now, let's look the request flow. We get a GET request in our app server. We directly look up in our Redis cache. We see, do we have this code? It says yes, the cache hits, because that could be one of the popular link. We return back the long URL. We never touch our main database, right? That saves massive amount of hits that your database might be having with those skewed traffic, where one request is seeing much more traffic than the others. And let's say if there's a cache miss, we'll update our Redis, and that request will hit your database. Then the cache will be populated with that, and then we'll return back 302 redirect. Now we can have LRU as a eviction policy, which is like least recently used. When the cache is full, we'll drop the link that nobody clicked recently, which is pretty obvious, straightforward. So for URL traffic recently clicked, it's a good proxy for will be clicked again, right? And TTL we can keep for 1 day, which is like plenty enough. And LRU will handle the rest of the eviction of least recently used. Okay, another possible dive deep would be on the custom alias support. This can be tricky, right? Custom alias is something which might need to handle it separately, because auto-generated codes will never collide. I mean, it gives you the guarantee that every long URL is mapped to a short URL, and that's a unique constraint over your database as well while you're storing in your PostgreSQL. But custom alias have a fundamental problem, because two user might be asking for same alias, right? Which is a problem. You might need to decide whether do we need to solve this problem at the application layer, which is your app server, or do I need to solve this problem at the database layer? I want someone from you to answer this problem in the comment. Would really appreciate that. Now we'll put together everything that we discussed. We have a client, we have our post request, which is like create mappings of long to short. We'll see around 3 QPS. Get request around 3000 QPS. This is our servers handling all the business logic. Then we have a Redis, which gives you the next counter, which basically increments and returns back the ID. You use that ID to generate base 62. Then we'll do the get paths. For every get request, we'll look in our Redis whether do we have this mapping or not. If we have, we skip the entire call to our database, return directly from here. If it's a cache miss, we'll update our Redis, return the response from Postgres DB. Yes. You may notice here that we didn't do nothing fancy. No sharding, no message queue, no dedicated ID service which you might see in others' video or other solutions. This is like a very simple version of every component that we are seeing is enough for this problem statement that we had, even for the scale that we discussed. And being able to say that loud in the interview rather than drawing those extra boxes is a green flag. Also, let's quickly have a look on the schema that we'll be storing in our Postgres or any kind of DB. One is the ID, which is your primary key. Basically, it's the counter value, which gets converted to a base 62. The short code that after the base 62 conversion, original URL, which is the long URL, created at, which is the timestamp when it was created, and the expiry. Also, let's quickly see the API endpoints. I know we should have discussed this in the starting of the interview, but since the API endpoints were straightforward, I would rather do it in the end, but you should be doing it very first, because this was like tutorial or more like learning session. Let's see the post, which is like create mapping, which is long to short mapping. The request would look something like this. You have an original URL. If there's a custom alias, we'll populate that. Let's say Diwali sale. If there's an expiry, again, which is optional, we'll populate that as well. The response might look like we got a short code, this is a short URL, original URL, and expires that. You can debate and reduce the response size as well. Just returning short URL is also fine. Then the other could be 400, which is like invalid URL, which is like we were not able to process. That was invalid. We some special characters, something. 409 could be alias taken because we want to handle the custom alias. 429, which is rate limited if someone is trying to DDoS or someone is trying to. 429 is like rate limited throttling. Whenever anyone is trying to DDoS or anyone trying to exploit, trying to send unnecessary heavy requests to you, he'll throttle them, kill switch. Then the get request will send the response. 302 will send the location as well, which is the long URL after the lookup from our database or Redis. That's it. 404, which is not found, or 4010, which is expired. Perfect. So that was all that I wanted to share on this problem. There could be multiple follow-ups as well, which I have mentioned in my blog here. If you scroll it down, follow-up questions, which essentially we have covered everything by a counter, not just hashing the URL by 302, 301. It's a very in-detail discussion here as well, which you can read it out loud and understand how do we design such easy and sometimes complex. Perfect. So that was it. If you liked the video, to like, share, hype, subscribe, comment, and that motivates me to come up with more such interview problems, system design interview problem, maybe easy, hard. Just let me know which one you want me to cover the next. Thank you. See you. Bye-bye.